what I'm hoping to do is make these sessions a little bit more, back and forth as opposed to just me talking at you guys. So it would be nice to, maybe what we can do today is just go around. I was hoping if there was some more people, this might be a little bit more interesting, just to go around and do some just introductions real quick, just, name, affiliation, and just what your interest is in Corundum. Is just, interested personally, or you want to do some research around it, or trying to use it in a product, or I don't know. That would be just interesting to hear from you guys. And then I got my slides, and then I think there's a couple of things that that I'd like to discuss. So, all right. So somebody want to? I guess I can kick it off. I'll go first. My name's Alex Frensich. I am a postdoctoral researcher at UC San Diego. I mean, I made Corundum, so that kind of answers that part. But at UCSD, we're going to be using Corundum for data center networking research and optical switching research. So I'm working on the core logic now, but soon we're going to be doing a lot of application level work on top of that to facilitate the work that we're doing here. All right, so let's see who wants to go next.
I could go. Hi,
Okay.
My name is Alex Bada, and currently just looking. I guess it's a personal interest, and I'm mostly interested, I guess, in the PCIe portion of the project, because that's something I haven't worked too much on. So it's interesting stuff to learn. For now, just observing from a distance.
All right. Nice to meet you, Alex.
Yeah, maybe I can go next. I'm Jiaxing. So I work with Professor Aditya Akela, and now I'm in UT Austin. I'm the third year PhD student. And last year, I have used Corundum to finish the project named Panic. And what I have done is just add some programmable hardware traffic scheduler and some offload engine into Corundum, and add a crossbar into Corundum to do some interesting offloading there. And the current project I'm working on is also related with Corundum. The basic motivation is there are many centralized CPU scheduling paper recently. For example, they are using an IO kernel-based approach, using a software dispatcher on the host to spread network load to different worker cores. And what I'm currently doing now is to offload the dispatcher onto the NIC. Or the Corundum seems already support the RSS, but different with RSS, which use a random hash to spread load to worker cores. I'm going to monitor more fine-grained workload on the host and monitor some interesting signal like cache utilization, memory utilization, queuing inside different workers to do the workload dispatch. So this is what I'm currently working on. Yeah, I'm done.
Okay. Yeah, that sounds like a super interesting project.
Actually, one thing currently I'm working on, because we want to do centralized scheduling on the NIC. One interesting problem is we also want centralized buffering on the NIC. So maybe we will end up using the on-NIC DRAM to store those packets, or we will eagerly first push the packet data onto the host memory and left the descriptor onto the NIC for scheduling. So that's an interesting design we are currently in.
Yeah, for some of the stuff that we're doing at UCSD, we're also going to be buffering on the NIC, either in HBM or DRAM, depending on what the card supports. So hopefully we'll be able to get the memory interface up and running soon and connected to the application section. Sounds like you might be able to make use of that. Yeah,
I'm thinking, is it currently the DMA engine is connected with SRAM, with a RAM on the NIC. So is it possible to replace that RAM into DRAM to store the packet before sending to the DMA? But I guess there may be some performance issues.
Right. So eventually what we're going to have is the unified DMA infrastructure. So you'll be able to use the DMA subsystem to access not only the host over PCI Express, but also whatever on card memory is available. So either HBM or DRAM or whatever. that's a little ways down the road before we have all that integrated, but that'll be the idea. You'll be able to, send and receive packets from host memory or from on-card memory
Yeah.
using the DMA infrastructure.
Yeah, that sounds good.
All right, I guess we just have Alberto and Andre.
You can go first.
Oh, I was going to say the same thing. Okay.
Okay.
So yeah, we work together. So Alberto Lerner, I'm a senior researcher at the University of Freiburg in Switzerland, and we actually are involved with data analytics, data processing, data management in general, and we are coming from a very positive experience with Tofino-based switches. So Tofino switches allow us to move application logic into the switches, into the network, and we were capable of, so to say, like extend where we run our database, our data analytics tools to inside the network as well. Our tools don't stop at the network card; they go all the way to the switches as well. And of course, in this first time, we jumped the card. But we missed. We have a number of things that we would like the card to do for the data analytics, the data management as well. So this is the idea, to allow the database to cover the logic, the database logic to cover the NIC and the switch as well. We're relatively new to FPGA. We've been doing we come from software. We're using the opportunity to do our conversion as well, having a lot of fun. Very pleased with the way the Corundum code base is organized. Thank you, Alex. Yeah, so there's a bunch of data analytics that we want to move into the application, and we think that the running certain processes in the card can make a gigantic difference between running them on the host.
Okay, I'm Andre Wieser. I'm a student at the University of Freiburg. I work with Alberto, so everything he said. So yeah, we're mostly looking at like co-designing databases and hardware, right? And especially also RDMA, like looking at like making RDMA better for database systems.
All right, great. Well, great to hear from all of you guys. Sounds like everybody's got some interesting stuff that they're working on. All right, so I'm going to go ahead and pull up my slides here. One moment. All right. Okay, so there's just a couple of things that I have to talk about in the presentation today. The first thing is the integration of the application block, which I'm sure everybody has seen the repository. Pushed a huge amount of code up there that's ported all the designs over to using this new kind of shared core logic, and also added the capability to more easily incorporate custom application logic. And then so there's still a few loose ends that need to be tied off with respect to that. So some of those at the moment don't have a good idea exactly what that needs to look like. The other thing is the shared interface data path. This is what I'm going to be working on over the next couple of weeks here. The idea is to kind of reduce the resource consumption footprint a little bit by sharing the data path between all the ports on each interface. So I'll go into a little bit more detail about that in the next couple of slides. Anyway, so for the application block, I went over the details of this at the last meeting a little bit in a bit more detail. But the idea is to add custom logic to, or provide kind of a nice way of adding custom logic to Corundum without having to go in and make low-level modifications to individual target designs or whatever. So it'll make it easier to run application logic across, multiple different boards, and also easier to update the, Corundum core logic without having to, merge a bunch of changes with, whatever you might have modified. So this provides kind of a standard set of interfaces to the application logic, including PCI Express bar for control via AXI Lite, interfaces for streaming data that connect to the Corundum data path, so you can deal with, receive packets, transmit packets at a couple of different levels. Then we have a connection to the DMA subsystem. So if you need to access host memory, and eventually that'll also be connected to, any on-card memory, through the unified DMA subsystem. And potentially a few more. I know right now it's also connected to, the PTP clock and whatnot, but we could potentially connect other things as well. So the version that we have right now is kind of an initial version. There's definitely a few things that are going to change about some of the interfaces that are provided, but it's integrated. You can use it on any of the currently supported FPGAs and FPGA boards. But this is only integrated on the HDL side, basically. On the driver side, we haven't done anything particularly complicated. I think right now we're basically just mapping the PCI Express bar. So that's available in kind of the core device structure, but we're not doing anything else with that at the moment. And this is the one thing that I don't completely have my head wrapped around exactly what this is going to have to look like, because I can envision a few different use cases. So I'm not sure what people are mainly going to be interested in doing. So there's kind of 4 different modes that I can think of at the moment of how an application, might work inside of the application section. The first one is that maybe it's completely self-contained. You don't need any, additional control logic or anything, in which case you don't even need the PCI Express bar. So you don't need any configuration or any integration of any kind. The next step up is, maybe you want some just register access from user space into the application section to configure things or to monitor things or whatever. You don't need a kernel module, you don't need any kernel code, but you want to be able to poke at it from user space. So right now we don't have a way to map that from user space, but it would be pretty simple to add, to modify the current mmap handling code to, support mapping the application section the same way you can map the, the rest of the registers from user space. So that's not a big deal. The next step is, okay, what if you wanted to run some kernel code? Ideally, what I would like to be able to do is put the kernel code in a separate module, so you don't have to modify the, the main kernel module. The idea here is kind of the same as having the, the separate application module, where, it makes it easier to update the core device driver, the core, HDL code without having to, synchronize a bunch of changes or whatever against, your own copy of it. But there's a question of, what sort of access that would need into, other components in the driver. Would we have to add a bunch of hooks? And also there's a question of, how the connection would be made between the two. Presumably this extension module would have to register itself with the main kernel module, which can then detect which application module is, installed on the FPGA and attach the appropriate extension module. So I don't have the details for that figured out yet. If anybody is interested in using it in that way, it would be great to have a discussion over, what sort of access you would need to, the rest of the system. So we can make sure that whatever we do here works for everybody's applications. And then the kind of the final integration method is, you want to do something fully custom. So, you make a copy of the driver and you change the PCIe ID so it attaches your driver instead of the default one, and then you could do whatever you want. So if we can't provide the hooks that you need for whatever reason, you always have that option available. So yeah, I don't know if anybody on the call right now is interested in, doing some complicated connections with the application logic, but this is definitely something that, it should be discussed at some point. Right, so moving on for now, we have the shared interface data path. And this is, when we started thinking about running RDMA on Corundum, I realized pretty quickly that one of the things Corundum supports is, multiple ports on one interface. And if we're going to keep that feature around with RDMA, we're going to have, kind of one entity that's performing all of the RDMA operations, because we have, because for RDMA, you have a bunch of, connections staked and whatnot. So if you have one entity that's doing all of that processing, then it makes keeping track of all that state easier, versus if you have your data path duplicated across across all the ports, then you have, you have 4 ports per interface, and you have 4 different entities that are doing this, and building in, 4 or 8 port memory for all of the shared state is not really a feasible thing to do, I don't think, for implementing this on an FPGA. It makes a lot more sense just to centralize it. And there's a few other advantages as well in terms of reducing resource consumption and whatnot. So the idea is we're going to pull all the data path components out of the kind of port level module. We're going to move it up one hierarchy level into the interface. So this is, the per port scratch pad RAMs, the streaming DMA engines, the transmit and receive engines, and the transmit and receive pipelines. I'm going to pull all of that out and put that at the interface level. So each port is basically just going to have a dedicated transmit scheduler and dedicated TX and RX FIFOs, and that's it. And then it'll be connected up to the shared logic. But when you do that, at least in the transmit direction, now you open up the door to headline blocking. So we have to implement some sort of flow control to make sure that you don't overfill those queues, because if you do that, then traffic going to port number 1 is going to block data going to the other ports until that queue drains out. And that's obviously something that you want to avoid. Additionally, we want to be able to add support for traffic classes. So this is going to be required for PFC, but could have other uses as well. So, and PFC is something that we're going to want to have available for running RDMA. If you want to actually do this lossless, we need the ability to pause certain traffic classes. So by having FIFOs on here that can support several different traffic classes, then we can pause those independently and make everything work. Let's see. And then, so I mentioned this before, that by using a shared data path, it's also going to reduce the resource consumption, and it will hopefully, well, it's also going to be necessary for implementing RDMA by handling all of this shared state in a more centralized way. So this is real briefly the block diagram of kind of how things are currently implemented. We have the on the FPGA, we have 1 or more interface modules. Inside of each interface, we have 1 or more port modules, and then these are connected to the actual transceivers on the board. So just as an example, most of the boards that we have right now, they have maybe 2 QSFP28 interfaces. So what you could do is have 2 interface modules, and then each one of those brings up a single 100 gig port on a single QSFP interface. So that would be 1 port per interface, pretty straightforward. But if you were running at a lower speed, say 25 gigabits per second, you could have 4 ports on each QSFP28 that all show up as the same Ethernet interface. And then you can change the basically the transmit scheduler settings to determine what traffic gets sent out of those 4 different ports, and you can hook those up to 4 different network topologies or whatever. It opens up some network architecture possibilities that aren't really supported with a lot of other NICs. So that's an important capability for some of the work that we're doing at UCSD. We need the multiple uplinks. So we need to keep that around. And what we want to do is, like I said, pull out a lot of this common logic, the transmit receive engines and the DMA engine, and then leave the port specific stuff in the port module. So this is kind of what it's going to look like. We're going to pull out data path, and then the port will just have the transmit scheduler and the FIFOs. This is probably not the most accurate drawing of what the FIFOs are going to look like, because the idea is to use something like a shared memory FIFO, where it'll kind of be a combination of you know, a large on-chip RAM for storing all the data, plus all of the multiplexing logic and whatnot. And by doing it in shared memory, you can more efficiently utilize the memory resources on the FPGA, and you don't need potentially as much multiplexing logic. You know, it'll when I'm talking about shared, it's just going to be shared in the interface. Each interface is going to have its own instance, but it'll be shared across all the ports on that interface. Right, so that's kind of what it's going to look like. And I had a couple slides going into a little bit more detail about some of these aspects. So the first one is internal flow control. So if you have multiple streams following the same path, then that opens the door for head-align blocking. I think receive is not going to be an issue, but for transmit, that can definitely be a problem. So to prevent that, we need to use some sort of proactive flow control. So not ready valid, but some sort of credit-based flow control. So we can make sure that the scheduler doesn't issue a you know, a new transmit request if we don't have space in the output FIFO to store that request. And the idea is basically to limit the number of packets and bytes per traffic class per port. And this information will be provided to the scheduler, but it'll be enforced by the transmit engine. So the transmit engine will not accept a new transmit request from the scheduler if it doesn't have, you know, the credits to actually issue that operation. And then what we can do is partition the transmit FIFO space between the data path and hardware application. So depending on the application needs, you can, you know, lower the limits on the, you know, the internal data path, and, you know, set the limit that you need for the application in terms of what packets you want to be able to send. Or another option is you use different traffic classes. If you use, you know, one traffic class for the internal data path and a different traffic class for the application logic, then you don't have a problem there. But the other thing is the application logic will most likely have to report somehow if it drops or, you know, reroutes a transmitted packet, just so the flow control logic works correctly. Otherwise, if you run out of flow control credits, then things will get stuck. Maybe there's another solution for this. We'll have to think about that once things start working. Let's see. Next thing I've mentioned this a couple times is traffic classes. These are required for PFC. I mean, if you don't have traffic classes, then you can just implement pause frames that pause everything. But PFC, the idea is that you can pause some traffic classes while letting other traffic classes through. And the traffic classes, they allow you to prioritize data. So if you're currently, you know, reading some packets and you want to send something a higher priority, then you can potentially, you know, get those on the wire first. And then obviously for PFC, you can pause the different traffic classes independently. And in this case, the scheduler will determine the priority, and the scheduler will get per traffic class flow control feedback. Unfortunately, I can't think of any way to make this work if we're doing, you know, some sort of dynamic classification of packets. So what's going to have to happen is you're basically going to have to assign different queues, you know, different priority levels, which I think is a reasonable thing to do. Well, at least this is for packets coming through the data path. If you know, packets coming from the application section, you know, you can make that determination however you like, and then make sure you're looking at the correct flow control counters when you send the traffic. And to implement traffic classes, we're going to need separate transmit FIFOs per traffic class per port. But I think if we use shared memory for that, the memory requirements won't be too crazy. All right, and then I mentioned this a couple times before that the shared memory FIFOs is what I'm going to use for you know, merging all of the incoming RX data and for handling all the outgoing transmit data. The idea is that we're going to have multiple FIFOs that are sharing a memory block, and you get some savings here because you can more efficiently utilize the block RAM resources that are available, or ultra RAM resources, as the case may be, depending on what device you're running on. Let's see. So the way these work is we have one relatively large block of memory inside the FPGA. We partition the address space into regions for each one of the FIFOs. And then on one side, one of the ports that'll be used for, the internal data path, and that's just going to be a single port that doesn't have to be shared. And then on the other side, we'll have, the second port on the memory that'll be used for, facing the Ethernet max. And in that case, we'll have to, arbitrate between, a couple different entities accessing that. But the idea is you'll have a different bus width, so you'll have an effective speed up. So for example, you might have 4 ports, each running with a 64-bit interface on the MAC side, on the wire side. But then on the interface side, you would have, 4 times 64 bits. You'd have a 256-bit interface. So you shouldn't have a bottleneck in terms of the throughput. The main thing to avoid with these, the main thing to worry about is that, the head of line blocking. Now, one thing I'll mention as well is that you can't do an async FIFO this way, or at least you can't do, each port on the memory only supports 1 clock. So you can't have 4 different receive clocks feeding into one of these things. So you have to use a separate async FIFO for each port, and that's already implemented in Corundum right now. That's one of the changes that I made, as part of the integration work that I did with the application section and whatnot, because I went ahead and split that out specifically with this in mind. So yeah, the idea with this is we'll be able to support, per port, per traffic class pausing, and also we'll be able to report, the size of those queues for this statistics collection logic. And, you'll also be able to, read that out through control registers and whatnot. So this is what I'm going to be working on over the next couple of weeks. And, once we get that squared away, then this will be a change to the interface with the application logic. Once this is implemented, then if you've looked at the application logic, there's like, I think 3 different sets of streaming interfaces. 2 of them are kind of on the Mac side. One of them is like directly connected to the Mac. One of them is what we call the synchronous interface, which is, synchronous with the internal logic, but it's still on the Mac side of the output FIFOs. And then there is one more interface for kind of the interface side, which is, closer to the interface. And that interface AXI stream connection, that's going to be converted to, a single streaming connection per interface, not per port. So you'll get all the traffic for all the ports on that interface through that AXI stream connection, identified with the TID field or something like that. So that's going to be a significant change, but that's going to be part of having this shared data path. All right, so that's all I got in terms of the slides for what I'm going to be working on. It looks like, let's see, it looks like Alex Badea posted something about, let's see, talking about EBPF, application extension hooks using EBPF. Yeah, so the thing is, there's definitely a, at least there's one group that I'm aware of that's been doing some work with EBPF, and they're using Corundum as well. So I'm hoping to have some collaboration with those guys at some point to try and, maybe pull some of that functionality back into the Corundum device driver. But yeah, I don't know about as an extension or as an alternative to the extension kernel module. That's an interesting idea. So
just from the wild ideas department,
yeah, so
I don't have anything
what was that
concrete
group anyway? That was the guys at the Axbrid, right, that are working on the HXDP. I don't know if that's ringing any bells, but they had a presentation at FOSDEM earlier this year where they were talking about kind of the progress on that project. And I guess previously they were running on the NetFPGA Sumi. And I think the paper they wrote was running on the NetFPGA hardware, but they've been migrating over to Corundum apparently. So I don't know exactly what sort of capabilities they've added to the driver, but they're more talking about actually running eBPF code in the hardware, which certainly an interesting capability. But it seems like you're more talking about writing extensions in eBPF, which is maybe a slightly different thing. So that's,
Yeah,
I
it
guess
would be.
that's possible. Unfortunately, I'm far from an expert in eBPF, so I don't know what that would require in the on the driver side. To be honest, I'm much more familiar with the HDL side of things. I'm very new to kernel module development. It amazes me that the Linux, or that the kernel module I've put together for Corundum is able to run anywhere near 100 gig line rate, because that's like the first kernel module that I've ever written that's like a non-trivial kernel module. So I've learned a lot by looking at the Mellanox device driver code, but if I need to do something that's not already implemented in there, then I don't really know what that would require. So do you know more about eBPF? Is that something that you've used a bit?
No, I'm myself trying to catch up with EBPF because they're moving at a lightning speed. But what I have in mind, for example, you can do, I guess, genetic kernel tracing with eBPF that has nothing to do in itself with networking. And you can do eBPF helpers that do, I don't know, statistic gathering and so on. So a bunch of logic that could be in eBPF. So I'm thinking maybe that's a possibility of to do something on the kernel side for the application blocks.
Right.
And
yeah,
I guess
I think it depends on kind of what the application is, because you can definitely attach eBPF stuff to just sending and receiving packets, and that we could probably support that in the generic device driver right now without any connection to the application section. There's also XDP sockets, and it would be nice to support those at some point. I think the main thing that we're missing right now for something like XDP sockets is some sort of flow steering in the receive direction. But yeah, neither of those really have anything to do with the application logic. Now, if you did want to have some sort of kernel component to interface with the application logic, I mean, yeah, I'm not sure exactly what that would look like. I don't want to presume too much about what people might want to do with that, just to keep it generic and to keep it flexible. But as I had on my slide, there's a couple of different levels that we could provide kind of or that people might want to use the application logic. There's the really simple ones where basically just provide register access. And then if you're trying to do something complicated enough, you can just, make a copy of the driver and make whatever modifications you want. But for that spot in the middle, yeah, I don't know exactly what that might look like. Now, in terms of eBPF, I don't know if that would be, kind of a sufficient replacement for a kernel module. But I guess a possibility that you might be able to do is have kind of a standard extension module which implements eBPF or something that you could then plug in your custom logic into via eBPF instead of writing your own kernel module. But I mean, that does raise the question, is it easier to write eBPF or is it easier just to write a kernel module?
I guess EBPF would give you a certain level of isolation, so it makes it harder to crash the machine. So for an application developer point of view, that might be desirable. But yeah, I haven't looked into the details at all, so it might just not fit.
It's an interesting thought. Yeah. Well, maybe we can take that one offline and discuss that on Slack or something like that. I was kind of hoping we would have a few more people that are interested in doing stuff with the application section to actually have a discussion today, but seems like you got a pretty small group, so we'll probably just have to have the discussion on Slack then, if this is something people are interested in working on. Does anyone have any other questions or comments about some of the logic that I'm going to be implementing in terms of the shared data path or the application section? I guess not really.
So one thing that comes to mind is one scenario is people doing virtual machines and using SRIV to pass through some of the ports in virtual machines. And I'm wondering if people want to do that, how would that look like with a shared data path?
Right. So that's a good question about SRIV. To be honest, I'm not super familiar with SRIV. I have taken a look at what that looks like on the PCI Express side of things, what the spec requires and whatnot. I don't have a good feel for how to handle that, on the FPGA side of things. I mean, it's certainly possible to, tag stuff based on, what VF it's associated with. And we could certainly set it up so that, certain VFs can only see, a subset of the queues or whatever. But part of the issue with that is that, SRIV support is not on, our critical path at UCSD. So, there's kind of a limit to the amount of time and effort I can put into supporting that. So if SRIV is something people are interested in, I would be, more than happy to have some discussions on what that would look like. And, if we need to make any changes to the core logic to, help support that. But unfortunately, that's not something that I can implement myself. So is Alex Badea, is that something that that you're interested in, or that you might want to help with, or you're just throwing some ideas out there?
Mostly throwing ideas. I would be interested in looking at it, but that depends on my free time. So it's difficult. But yeah, I guess my point of view is it basically amounts to adding more hardware logic to help the VMs. So from a FPGA implementation point of view, there's just more work. You would kind of have to go in the opposite direction of basically dedicating a data path for each of the SRIV functions, and that seems like just more work in the FPGA. And I would probably look at some alternatives of giving VMs their data path, which would not use SRIV. That sounds like the easier thing to do, probably with cooperation of the kernel driver.
Well, I'm not sure each VM would need to have its own data path necessarily. It seems like the main thing that you would need to partition is, like the queue states. So each VM would get, its own, kind of grouping of queues, and then the data path wouldn't really care about, which VM the queues are associated with.
Yeah, I suppose some part of the DMA would have to be partitioned as well, because each of the functions will get their own address space.
Right. Yeah. So I think, so as far as I'm aware, if you're using SRIV, you're probably going to be using the IOMMU, and that's done on a per PCI Express function level. So I think all you need to do is make sure that the DMA requests are tagged with the appropriate function. So that would have to be tracked in the queue state logic along with the the ring addresses and whatnot, so that when you issue an operation from one of the hosts, that the corresponding DMAs are tagged with the correct function, so everything works. That would require some changes to a lot of different modules, but they're relatively minor changes to kind of thread those signals through. To be honest, that's not my concern. It would take some time to do that, but wouldn't be particularly complicated to implement. The bigger issues are, if you have multiple VMs running on here, you can't use just RSS across all the receive queues, right? Because you're going to have receive queues dedicated to different VMs. So you're going to need some more intelligent, flow steering logic to, based on the MAC addresses or the IP addresses or whatever, to route the packets to the corresponding VM. I mean, I think that's kind of one of the tricks with a lot of the NICs that support SRIV is it doesn't just support SRIV, but it also supports a lot of reconfigurability on the receive path, so that you can actually get the packets where they're going. This is where, you know, people might actually want to run P4 on a NIC, right? Otherwise, you might not really care about, you know, P4s for switches. Well, okay, if you have a bunch of VMs running on a computer, you kind of need a virtual switch on the NIC in order to, you know, connect everything up. Bringing some sort of P4 support into Corundum would be pretty cool. But again, that's not something on our critical path. So if there's somebody that wants to, you know, spearhead that effort, I would be happy to work with you and help make sure that it has all the right connections at the driver level and at the, you know, at the HDL level, but that's not something I have time to work on myself. So. Although one thing that would, I think, be good to implement is some sort of flow steering logic that's good enough for like XDP sockets to work. And potentially that could also give you some limited support for SRIOV. We may cross that bridge at some point. We'll see. Any other questions or comments? Oh, Justin, did you ever hear back from Xilinx about the those new boards?
Yeah, I believe so. I believe my professor has already heard back.
So you got a couple of boards on the way then?
I'm not sure whether they're on the way, but
okay.
Yeah, I believe maybe in the future.
Okay, yeah, I guess part shortage wise, who knows when those things are going to ship.
Yeah, that's
But
great.
that'll be good. A couple, I think what you're getting a couple of U280s, I think. So,
yeah.
Yeah, those are good boards. But I've been having some timing closure issues with those because of the way the SLRs are laid out. Spent several days last week screwing around with placement constraints.
Oh, so what's the problem?
Well, I mean, the issue is that there's 3 SLRs on there, and the bottom one is the PCI Express, or has the PCI Express hard IP, and the top one has the Ethernet Max. So there's nothing in the middle SLR, and crossing all the connections from the bottom all the way to the top. Apparently, Vivado is not very good at figuring out that placement. So, if I don't give it any placement constraints, it just kind of sprays the logic all over the device, and the SLR crossings end up in really bad spots, and the performance is terrible. If I add a bunch of placement constraints, then you can run into issues with just the placement, Vivado respecting the placement constraints a little bit too well. And then you have all the logic in the bottom and all the logic in the top, and then all of the signals that do have to cross end up crossing 2 SLRs. So I've been trying to add some pipeline registers to a couple of things, but it doesn't necessarily help as much as I would like. I don't know. Let's see. I think so. One of the new features that I added with the most recent set of updates is I added these pipeline FIFO modules, which allow you to do, you know, somewhat lower overhead, you know, long distance connections with lots of pipeline registers in the middle. So I have those set up for kind of the transmit and receive data paths, and for handling the receive PTP timestamps. And those seem to work okay for crossing that middle SLR. But the issue is right now we have to get the basically current PTP time from the bottom SLR to the top SLR. And that's a bit of an issue. I've been trying to add some pipeline registers to a couple different modules, but the trick with that is you have to do it in such a way that you can basically compensate for the skew that's added by those pipeline registers, right? Because that's going to delay the timestamp. So you have to either subtract that out somewhere, or, you know, set up whatever feedback loop you have such that it compensates for the added delay of those registers. And the couple times I've tried to do that, Vivado is, merging the registers together and whatnot in ways that I wasn't expecting. It's like Vivado is more geared towards optimizing logic that ends up being, clustered together in one spot. If you have logic that's spread out across the chip, it'll figure out if you have a really high fan out signal, and it'll replicate, flip-flops to try and, reduce the fan out. But if I have a flip-flop that's driving two targets, and one is here and one is two SLRs over there, even though you could duplicate the driving flip-flop and, move it a little bit closer to one of the destinations, Vivado is not smart enough to do that. So,
Okay. Yeah, this sounds annoying, but
right. So
hopefully we can solve it.
Well, so it is a little bit annoying, but the other thing is, like, if you add a bunch of application logic that sits in between the Mac and the kind of the core FPGA logic, it actually ends up being kind of a nicer arrangement, because, on the bottom you have PCI Express, in the middle you have your application logic, and the top you have the Ethernet Max. Everything's nice.
Yeah, I believe that will be
like I think the U250 or something, the PCI Express logic is more in the middle. So you can have your Ethernet interfaces up here, your Corundum logic, and then when you put your user logic down here, so you got to go all the way down and then process it and then back up. It's like, I don't know.
Yeah, I believe, like, if I add my custom logic, things will become better.
Yeah, so putting the custom logic in there may end up being, more useful, but I don't know. I'm gonna continue hammering on that and see if I can improve the situation a little bit. Obviously, close is better at 10G most of the time, because the clock speed is lower for the 10G max, 156 versus 322. So you get a little bit more flexibility. But yeah, all the other boards seem to work pretty well. The ones I mainly have issues with for timing closure are the the multiple SLR ones, or the slow ones, right? So the Exynos X10, which has a Kintex Ultrascale, or the NetFPGA Sumi. And I think right now that's failing timing just barely, because it's got a Vertex 7, a rather old and slow. So yeah, but that's one thing I try to do every time I push stuff to the main Corundum repository, is to go synthesize it across all of the target boards, so that I can catch any timing related problems and try to sort those out. So if it doesn't close timing on something, that's just going to cause headaches when people that are using the code try to update it. Flip side is I make no guarantees on whether your application logic is going to close timing. That's on you. All right. Okay, so any other questions or comments or anything people want to discuss at this point? I think we're pretty much at time here. All right, I guess if we have nothing else to discuss, then we'll go ahead and close it down, and we'll see you guys in in 2 weeks for the next one. Thanks to everybody for tuning in.
See you.
Thanks. Bye.
Thank you.
See ya.